Now can you hear me? There we go. Okay. So, got a ton of questions in an email this morning, but before I get to that email, those of you in the Friday 251 lab, it is most likely going to be canceled tomorrow on account of ice and snow. The school has not officially put an announcement, but we definitely got our emails today saying, by the way, if it happens to be canceled, this is what you need to put in your emails to students. State has not officially called, but they are officially calling, they're officially telling faculty and student health that, yeah, they're going to be closed tomorrow. We're also probably going to see Wake County Public Schools closed tomorrow, so yeah, there's like a 99% chance that we're not going to have the lab tomorrow. Since that is most likely the case, again, we haven't officially called it yet, but I've already set the announcement up because I'm pretty sure that's what's going to happen. If we do end up being canceled, most likely we will. 251, you've got the molecular modeling without naming. That's in your lab manuals. If you don't have a copy of your lab manual, send me an email. I can send you an electronic copy. That you need to complete on your own and submit that to the course website next week. You'll see an email about that go out tomorrow morning. Should be about 8 a.m. when it pops up. I will be having office hours, but they'll be done through MS Teams, so I will be on MS Teams. Just send me a message if you have questions. As far as the lab itself, I'm going to let you do this asynchronously, so you can do this on your own time, but during the lab time, I should be available by email or by MS Teams. I'll be getting a lot of work done tomorrow anyway, so big thing I'm not doing tomorrow is streaming any of this. There are a lot of issues in terms of like protecting your identity. If I stream this, how do I make sure that only certain people have access to the video? Short answer is it's a ton of work, and it's just a ton of work. So there is nothing going to be streamed, but if you chat with me, we can do video if it's really necessary. But again, like you'll have that option through MS Teams. I'm just not going to set up any type of formal event because it is kind of a lot. We can't really record the event, and particularly with MS Teams, what I found is the bandwidth gets really narrow really fast. And so in order for me to like put something meaningful on the board behind me or to write something or show you something, the image quickly gets degraded simply because MS Teams isn't good at handling a whole bunch of videos. All right, now to the questions I got asked. These are all out of 252. Looks like a dozen or so questions about, I'm going to assume the study guide here refers to the homework. So first one, question 13, draw the principal organic product from the reaction of benzyl bromide. This is this compound. Poorly drawn, but it is this compound with, looks like sodium ethoxide. So this is one of the few nucleophilic substitutions you'll see with a benzene ring. This goes in, pumps it, pops the bromine out, and we'll end up with an anisole derivative, which is ethyl benzyl ether. And let me just check to make sure I'm right. Benzene does not like to do a lot of these nucleophilic substitution reactions. It's actually quite difficult for benzene to do this. Your book kind of presents it as a thing that happens. It can, it's just not really common. Big reason is that benzene ring is actually pretty electron rich, and so there's not a lot to really drive that ethoxide to attack it. That said, it can happen, particularly if you have a good leaving group like bromine. What's up? So it says I'm wrong. Of sodium ethoxide with benzyl bromide. Oh, damn it, this is really annoying. Not phenyl bromide, benzyl bromide. Sorry, my mistake. So we'll end up with a benzyl ether. So there actually needs to be one more carbon in there. Yep. All right, next question. Question 14. Give the structure of the principal reaction of benzyl bromide with sodium hydrogen sulfide. This is going to be a very similar reaction. Sodium hydrogen sulfide is just SH minus, and instead of getting an ether here, you'll get a thiol. So these are just nucleophilic substitution reactions. They'll occur a lot more for this primary carbon than they will for the benzene ring itself. 19. The following reaction has been reported in the chemical literature and gives a single organic product in high yield. Write the structure of the product, the reaction of 2-phenylpropene. Treat it with diborane and tetrahydrofuran, followed by oxidation with basic hydroperoxide. So this is hydroboration oxidation. So your 2-phenylpropene. Situation where IUPAC naming. So propene is this molecule, and then your 2-phenyl. This molecule, your hydroboration, B2H6 and sodium hydroxide, followed by peroxide treatment, or diborane and tetrahydrofuran, THF, still your solvent. And the basic sodium hydroxide is they're putting the NaOH down here. This is an anti-Markovnikov hydration of this bond, and so what we should get this molecule here. That's correct. All right, 21. Give the structure of the expected reaction of isopropyl benzene with sodium and ethanol and liquid ammonia. So this sodium here is going to create your alkoxides. Excuse me. So we have isopropyl benzene. And liquid ammonia, sodium and ethanol. So this should be an ethoxide. I'm curious, this is looking like an actual nucleophilic substitution, and I don't know why this would happen. Isopropyl benzene with sodium and ethanol and water. So if I had to guess, I'd say you make this. So let's see what it happens. Oh, sorry, it's not ethoxide. This is Slimmy. That's why I didn't recognize it. Because I was just talking to someone. This is a Birch reduction. So with the Birch reduction, you get rid of one of these double bonds, and you end up forming. They're going to say it attaches here. I have no doubt the key will also include it if you attach it there. But this is just a Birch reduction. So with the Birch reduction, what you're doing is you're breaking the benzene ring, and instead of starting with your 1,2,1,3,5 cyclohexatriene, which is what benzene is, you end up with the 1,4-hexadiene instead. So this is just a Birch reduction. I did not recognize it. 22. Get the product reaction of isopropyl with sodium dichromate, water, sulfuric acid, and heat. So this is looking like, so this is a reaction you can do with benzene, not particularly common. It is shown in the notes though. This is just basically a harsh oxidation. Harsh, H-A-R-S, like literally just means like hard or aggressive oxidation. So with these types of reactions, if you have an alkyl benzene and you expose it to very strong oxidizing agents, so in this case, this is Jones reagents, you will end up producing the carboxylic acid. So basically, your strong oxidizer here burns off everything but the benzene ring. I think in the notes it talks about doing it with just toluene, which will give you the same outcome. All right, get the expected structure of the product of isopropyl benzene with N-bromosuccinide and CCl4, heat, and benzoyl peroxide. So your NBS here creates a free radical and brominates the product. So what we expect to do with any type of free radical is substitute the most stable, a tertiary over secondary over primary. Particularly, this is an allylic carbon. It is beside the benzene ring. So my guess here is that we'll replace it with bromine, and checking the solution. Yep. So all this is NBS applied to any, in this case this ends up being allylic. But this would be free radical halogenation, but the case of NBS are actually quite selective to only doing like the tertiaries and only doing it once. 24. So we have the following molecule. They're actually using dotted line this time. So, I think the confusion I'm seeing with it, so this second question is just hydroboration oxidation. This is an anti-Markovnikov addition of an alcohol. It's not going to require you to specify the stereochemistry, although both the R and the S pairings of these are going to show up. This is just kind of alkene review, and that's why these questions are in here, is to make sure that you kind of remember how to do basic reactions of alkene. Now, a thing to keep in mind with, it is going to make you specify that it is the trans. So you do need to draw that this has a wedge. And this is going to be on the opposite side of it. So you are going to need to specify the stereochemistry when you start doing this problem. But again, this is just hydroboration oxidation. There are still reactions of alkenes going on. The big thing to keep in mind of reactions of the alkenes is that the reason why we're looking for aromaticity in these compounds is the aromatic rings don't react. Those double bonds don't react. So you can do electrophilic aromatic substitution to aromatic systems. So you can do this to benzene rings, anything that meets our 3 criteria, that's circular, conjugated, meets the 4+2 rule. But something like B2H6, hydroboration oxidation, any additions, those are not going to happen to these benzene rings. And this is 2 reasons for, so I keep writing this circle up here. There are 2 reasons for this circle. It's a shorthand to say that this is an aromatic ring, and the second is that it kind of takes the double bonds out of the picture, so you're not tempted to try and react them away. (26). So draw the following reaction as prescribed literature, gives a single organic product. This is H2SO4 and alcohol. This is just acid catalyzed dehydration of an alcohol. So again, we're just kind of refreshing of course it's going to get the stereochemistry. We're just kind of refreshing your memories on, with these types of problems on reactions of alkenes. Because especially with the dienes, the trienes, anything that's not an aromatic system, they can still undergo these reactions. So it's good to know that these reactions still occur. So this is just an acid catalyzed dehydration reaction. And what we'll end up doing is putting a double bond along the back, and then we'll have the benzene ring here off to the side. Make sure you can still see that. Now I have consulted the key. It's not going to like force you to like draw it this way. So if you want to, you can also draw it that way, and it will also accept as well. So you don't need to do the boat conformation, which is, it's kind of odd that it's showing it to you anyway. But yeah, that's all of this is an acid catalyzed dehydration. We'll get the alkene. In particular, the large driving force for that is that this does put these as a conjugated system. So this is why xylene is actually so stable. I'm sorry, not xylene, styrene. Styrene is so stable is because of that alkene that's conjugated with it. 27. Following reaction, we have potassium carbonate with Cl. It's an interesting one. It's a base. So my guess here is that you're going to produce the carboxylic acid. I'm not liking this question. Ooh, I don't like this question. So question 27, I'm going to drop it. This was a bad way to ask this question. Basically what you get with this reaction, I don't disagree with the product, I just think this is an obtuse way of getting to it. The bicarbonate reacts with water to give you hydroxide in the bicarbonate ion. So I agree with that. And then this hydroxide undergoes an SN2 reaction with the Cl, and so you end up producing the cyanophenol. I really think that's an obtuse way of asking that question. So I'm not going to, or not the phenol, produces an alcohol, but I don't like how that question's asking that. So yeah, I'll drop question 27. The following sets of reactions convert phenylacetylene to butylene. Give the appropriate reagents for each step of the sequence. So step 1 is we're converting this compound into this compound. We get to this by removing a hydrogen. Now it gives you an Na plus here as kind of a hint. So we can either do this directly with sodium, or more likely what we're going to do is we're going to react it with NaNH2. If we did just the sodium in the NH3, because the first one says NH3, we could end up forming this trans alkene. I should say trans alkene. We can reduce this down to an alkene. This is something that, you know, does happen. So I would say NaNH2 for the first step. And again, the reason why you wouldn't want to work with pure sodium here, sodium is more likely to actually, if you look at reactions of alkynes that we talked about in Organic 1, this is a way to reduce an alkyne to an alkene without going all the way to an alkane. All right, so we're going to take the product of this reaction. Negative. And we want to produce, we want to add an ethyl group. Easiest way to do this is nucleophilic substitution. So your anion will attack the bromoethane, dislodge the bromine ion. And so I'd say CH3 CH2 Br. And then for step 3, the last one, you're converting this to the alkane. That's a terrible way to draw that. This is just H2 and PT to make this happen. So the first one, there isn't a subscript. That's just platinum. The second one, H2. Yep, that's how it works. So again, we don't want to work with sodium because sodium will give us the alkene instead, so we want to do NaNH2. This is a super good base that will extract that hydrogen to give us the anion. The anion will undergo an SN2 reaction to displace this bromide. Now you will produce some amount of ethylene, but particularly with this isn't a great base. So you're going to get the substitution here to give you this complex, and then you just hydrogenate that bond away. So it's 30, 31. A single organic product was isolated after a Birch reduction of paraxylene suggests a reasonable structure for this substance. So, what is paraxylene? I'm guessing the reason why it picked paraxylene is that it pretty much guarantees you that you're going to get like one product. So now we have to draw the bonds in. Paraxylene, ortho, meta, para. So what happens with a Birch reduction is we can convert benzene to 1,4-cyclohexadiene, and then we need our methyl groups paired to each other. So 3 carbons apart. Now it doesn't matter, you have 2 options here. One where it's straight up and down, and one with an angle. If I remember correctly, this is the predominant product. So finishing with a methyl group on a double bond. From what I understand, reading up on this, the Birch reduction is actually not well understood. But yeah, this is the one it wants you to go with here, not the one where these are on opposite, or on the sp3 carbons, just the non-double bonded carbons. You need to put the one where it has the methyl groups on opposite side, on touching those double bonds. But yeah, for a Birch reduction, convert benzene to 1,4-cyclohexadiene, and then all your groups are still in the ring, and you can try to put as many groups on the double bonds as possible. 31. 32. Try 2 different resonant forms of the triphenyl methyl cation. There's your triphenyl methyl cation. And then once you write it as both an ortho and a para position, so the way we resonate, we're going to kick the bond up, give us a positive charge there. I'm going to represent these just as R groups. That'll give you a carbocation on the ortho position. We resonate by kicking that bond down, and that will give us resonance on the para position. So yeah, the challenge with this one, this is your triphenyl methyl carbocation. It's a weird way of saying it. It's actually easier than trying to name it any other way. So yeah, IUPAC tends to take a vacation when we start doing benzene rings. At least that's my remembering of Organic 2 in college. So your triphenyl methyl here, first resonance structure puts a double bond between that methyl carbocation, and that gives you the carbocation on the ortho position, and then a further moving that double bond gives it to you on the para position. 32, 40. Write a resonance form of pyrrole in which nitrogen forms a formal charge of +1. Are comparable resonance forms possible for pyridine? Be sure to include all lone pair electrons in your drawing. Okay, so pyrrole. So this is pyrrole. This is pyridine. Both of these are aromatic. This one is aromatic because the nitrogen and uses its lone pair in the aromatic system. For this one, the nitrogen does not use its lone pair. So the resonance form here, kick this lone pair down. And this will end up putting nitrogen with four bonds around it. This is how we end up with the positive formal charge. And we'll end up putting a lone pair here on one of the carbons, and this will end up basically end up giving us what's called a Zwitter ion. So this is a compound that has both a positive and a negative charge on it. Now for pyridine, can this happen? And the answer is no. So if pyridine throws that electron down, we'll end up getting nitrogen, first of all, with very strained double bonds in there. The second is that by doing this, we now have 2, 4, 6, 8 electrons. So this violates our 4n+2 rule. And so this ends up being anti-aromatic when we're done, but this compound here is aromatic. So for parole, the reason why this is aromatic is because those lone pairs are involved, and we can knock those lone pairs around the molecule to basically kind of like, I mean, that's what they're doing. The electrons are moving around. That's what makes it aromatic. That's part of the property of aromatic systems, is that those electrons are mobile. Here, if we use this lone pair and we put that +1 formal charge on nitrogen, we end up adding 2 more electrons to the ring, and this makes it anti-aromatic. So I would definitely say are resonance forms possible for pyridine? The answer is no. So you can't put nitrogen in a +1 formal oxidation state in pyridine, but you can definitely do it for anisole, or not anisole, pyrrole. And this is kind of how we have resonance around the ring, is because that lone pair is actually involved. 41. Predict the, draw the stepwise mechanism of the following reaction. HBr. This is, my guess, is an acid catalyzed dehydration. And there is a lot of good reasons for this to do what it does. But this may also be a substitution. My guess here is the HBr serving as a strong acid because there is a driving force to make the alkene. So with this, we have oxygen attack on hydrogen. This will break the bromine bond. This will give us our temporary hydronium ion, OH2+. This will let go of that OH+ to give us carbocation. This carbocation is actually resonance stabilized. So from the previous problem, you can get that, or a couple problems back, you can make this carbocation move around that ring. And then we'll get hydrogen abstraction. Give us a double bond. So basically, your bromide attacks the hydrogen comes down, and you end up getting the double bond. So I'm going to guess that. Let me make sure I'm right about the product before I start moving on. And most likely this is the trans product. So this doesn't seem to think it's going to form an alkene. It thinks it's going to form an alkyl halide. That works just as well. So for the alkyl halide, instead of this step where we do the elimination, we're going to have the bromide attack the carbocation. Yep, and pretty much everything I've got written up here is the mechanism. Just checking on my end. Yep. So this is the mechanism that follows. We have OH attack on the hydrogen. This causes the OH2, the hydronium alcohol to form. The OH2 pops off. We form the carbocation, and that's attacked by the bromide. (42). Draw a stepwise mechanism for, this is an ether synthesis. So what will happen first with this ether synthesis? We have a couple options here. If this were just an alkyl halide and we were doing ether synthesis, my speculation would be the oxygen attacks first. But if you look at the first step, it gives you CH3, CH2Br, CH3Br, HBr, and Br minus. So what's most likely going on here is that with our alcohol, we're going through an SN1 pathway. So our bromide's going to break off first. We're going to form the carbocation and the bromide ion. Next step, our ether or our alcohol. The lone pairs on the oxygen are going to attack this carbocation, and we're going to end up with this. Sorry, running out of board space here. This kind of hydronium complex, your bromide is going to pull that hydrogen back off, and you'll end up with the final ether. So first thing, SN1 pathway, the bromide's going to pop off. You're going to form this carbocation, but it's resonance stabilized by the ring. Here, the lone pairs on the oxygen are act like a Lewis base. They're going to attack the carbocation. This put a positive formal charge on the oxygen, and we're going to extract the hydrogen using a bromide to get us back to the ether. Now for the base, I am looking at the key to make sure this is correct. What it's going to claim is actually the other alcohol molecules that take that hydrogen off. This is kind of semantics. But it is going to claim that there is a second alcohol in the solution. That's fine. Basically the alcohol is the solvent in this case. '53. In intent to prepare N-propylbenzene, a chemist alkylated benzene with 1-chloropropane and aluminum chloride. However, 2 isomeric hydrocarbons were obtained, ratio 2:1. The desired N-propylbenzene, the minor component. What component do you think was a major component, and how did it arise? Actually, good question. So here we're going to assume one substitution, single substitution, or a single addition for the electrophilic aromatic substitution. And the trick here is they're telling you that this is 1-chloropropane. And they're working with AlCl3. So what happens? Well, the thing is that this AlCl3 here is going to generate a carbocation. And so if your intent here was that the primary was going to add to it, and this is what the chemist apparently thought, this would be nice, but this doesn't occur. What happens is we get carbocation rearrangement. And so we actually get attachment at the second carbon. So we get the isopropylbenzene. So the major product here is the isopropylbenzene because we get carbocation rearrangement with Friedel-Krauss alkylations if we're not working with either primary, if we're not working with secondary and tertiary carbons, or if we're working with an acyl chloride. All right, so the next step is going to ask you for the mechanism. So part 1, that's correct. You get the isopropylbenzene. From here on out, what happens is that so it's going to ask you about the mechanism. There's a lot in the notes about this. With the mechanism, what ends up happening is we break the carbon and chlorine bond when we make the AlCl4 minus complex. So what happens is that the AlCl3 basically jumps in and takes the chlorine off. This gives chlorine a positive charge and chloride a negative charge. So that's part of what's asking you is like, what are the charges on it? Don't know why it's saying aluminum is actually negative in this case. It's actually saying aluminum here is negative and chloride is positive. I think it's just an artifact of drawing the Lewis structure. 57. Succinic anhydride is the structure shown below is a cyclic anhydride you often use in Friedel-Crafts acylations. Draw the structure of the product obtained when benzene is acylated with succinic anhydride in the presence of aluminum chloride. So this is just kind of getting you to think about this reaction here. So in the reaction, this will occur. And what we end up doing is we cleave one of these bonds, and this R group attaches to the benzene ring through this carbonyl. Now in this case, the R group is just connected to the other side. So if this is just a carbon, what we end up getting is got 2 carbons. We end up getting this carboxylic acid. Now let's make sure it's not asking you for, yep, it's going to give you the carboxylic acid. So again, if you go look at the notes, it talks about acetic anhydrides being capable of also going Friedel-Crafts acylations. And what we end up doing, we prefer to work with the symmetrics, this way we guarantee what the product is. But we end up cutting one of these carbon oxygen bonds and attaching it to the benzene ring. So that's what we've done here. And then in this case, the R groups are just connected to each other. So there's R and there's R, and we end up forming the carboxylic acid on the other side. Question 60. Arrange the 5 compounds according to a decreasing rate of bromination. So how quickly they brominate. So this is going to be looking at a lot of things. So let's see here. We got M-xylene, orthometaxylene. Metaxylene. We've got benzene. We've got 1,3-trimethylbenzene. We've got toluene, O-xylene, and that's it. That's all 5. Relative rates are 10 to the 10 times 10 to the 7, 5 times 10 to the 4th, 5 10 to the 2nd, 60, and 1. So all these methyl groups are activated. They increase the rate of subsequent reactions. They're ring activators. So this is going to be our lowest one. So we're going to put this as number 1 as the lowest. Toluene only has 1 methyl group, so this is the second slowest. This has 3 methyl groups, so it's the fastest. Or this is going to be the fastest. The question is, where do these fall? So what we're going to look at here is where their directing groups are. So for this methyl group, it's going to direct here, here, and here. And this group is going to direct here, here, and here. So here, both methyl groups are reinforcing each other. They're making themselves much better at activating the ring at the same positions. If we compare these two, we have an orthosite here, orthosite here, orthosite, orthosite. Now you may sit back and say, well, this has more opportunities for alkylation or any type of reaction. I agree with you. But here, those opportunities are built up. So we have 3 spots here versus 4 here, but I'm willing to bet that these 3, because these 2 methyl groups are working to reinforce these 3 positions, it's actually going to work faster. It's not asking you who can be substituted more, it's asking who's going to substitute the fastest. So we're going to say benzene the lowest. 1,3-trimethylbenzene is the fastest. Toluene is the second slowest. Metaxylene is the second fastest. And orthoxylene is the third, and if I check it, it says I'm wrong. So I'm guessing I got E and A flipped. Okay, so it seems to think that this is actually the faster one because it creates more positions. Oh wait. Oh no, I put the wrong one in the wrong place. Yeah, it agreed with me. So this is the second fastest, and this is in the middle. So this is number 4 in terms of speed, number 3, number 2, and then number 1 here is the slowest. Sorry, just had them flipped. All right, questions from the packets. Pages 29, 30, and 33. 29. Actually, this is a really straightforward one. And yes, the key is correct. You can do this in 2 steps and you don't start the reactants out together. So what we want to get to is this para dicyclohexylmethane. So if you look at that, there's your benzene ring. And we can definitely get to this through using a double reaction through Friedel-Crafts alkylation. So if we add this plus, if we were to do an alkylation, we would want to do that halogen there, that chlorodicyclohexylmethane. That's how we would do it. And we can easily convert the alcohol to this alkyl halide through SOCl2. So your 2 steps: convert the dicyclohexylmethanol to chlorodicyclohexylmethane using SAlCl2, and then use a double Friedel-Crafts alkylation with AlCl3 in the benzene ring to give you that final product. Page 30. So 30, there is a typo on the final compound, but the hint here does give you a really good suggestion. So the final product here, and I'm going to eventually update this on the course website. I've got the key updated. It's just getting the time to go do all this. It is correct. These chloros are supposed to be opposite. But there's also supposed to be methyl groups in here as well. And you're starting with 2 things. This, and I'm going to draw the second one a little different. Okay, so 3 to 4 steps. I would entirely agree with that. Worked it out yesterday. Then I'll just start it together. And the big hint here is there's a Diels-Alder intermediate. So your Diels-Alder intermediate is always a cyclohexene. And if you look at this molecule, this looks like a chloro addition across a double bond. So if we have, this is the starting compound, this could be halogenated into this to get this final product. So far so good. This would be the Diels-Alder product. What would we have to run in order to get this Diels-Alder product? Well, we need styrene. So this would be your dienophile. And then your diene is this compound here. Both of these can be achieved by using tert butoxide on these starting molecules. So the way you do this, you use tert butoxide to form the diene and the dienophile. So you've got this diene, this dienophile. They will undergo a Diels-Alder synthesis reaction to give you this intermediate, and then you react this with Cl2. Now again, the key is missing, the product is missing the 2 methyl groups. I've updated that in a subsequent edition. I just haven't had time to load it to the website yet. 33. All right, so 33, this is also a Diels-Alder reaction. So we've got reactor 1, and we're charging it with ethylene and butadiene. And we've got a distillation column. And off the distillation column, we've got the lights, we've got the desired product, which we feed into a reactor 2, and then we've got the heavy components. And we're going to feed into reactor 2 with a stream of acid to get our desired product. So first of all, what do we expect to happen in reactor 1? Well, this is a Diels-Alder reaction, so we expect to form, particularly with this particular combination, 1-cyclohexene. Now, we're distilling it to get rid of any unreacted ethylene, and then we're going to react the desired product here, cyclohexene with the H2H+, so this should give you cyclohexanol. So far, so good. The question is, what's the heavy component? And the trick with this is to recognize that, and this is something that gets brought up in the notes, is that Diels-Alder is actually sometimes a little bit of a hard reaction control. The big reason being is that the product of a Diels-Alder reaction is another dienophile. So when you do Diels-Alder synthesis later this semester, we're going to have to start by distilling this compound. So when you run your Diels-Alder reaction, you actually have to start with dicyclopentadiene, and we distill it down back into cyclopentadiene. The reason we have to do that is that this will actually react with itself. It's a very good, the diene is also a very good dienophile. And the same thing is going to be true here, is that we're going to produce a product which has a double bond, and it will react with our Diels-Alder reagent to form this dicyclohexene. So if you react this with this under a Diels-Alder reaction, you end up getting this double ring. So how do you know this is what's formed? If you look at the carbon NMR, there's actually 5 NMR peaks. 1, 2, 3, 4, 5. And your last one here, since it's about 128 ppm, this is the bound range, this is the ppm shift for carbon 13 for double bonds. And these all sit in the 0 to 50 range, which is consistent for alkanes, CH3, CH2, and CHs. So the thing here was recognizing that, yes, while you were planning to reduce cyclohexene, cyclohexene can subsequently go back and react with your diene to give you this dicyco complex, which is your heavy component that you're basically going to have to throw it away. This is also why you would typically end up with excess ethylene, is that because this is reacting with this ethylene has nothing to react with. And this is not an uncommon situation, especially industrially, where you run something together and you'd like to distill one of the excess reagent back into the starting reactor because you don't want to throw it away, you don't want to lose it. And in this case, ethylene is really easy to distill off, so it's a lot easier to recycle. But because of this, you're probably running a 2-phase reaction. So this is definitely a gas, that's a liquid, this is a liquid. You're probably going to have issues with these two reacting with each other in the reactor because they're both in the same phase. This is a gas phase. This would probably be something like a bubbler where this would occur. And you're just going to end up with undesired heavies, but commercially this may be the most viable way of doing this. So congratulations to the student who sent me the email that took me 50 minutes to explain all the questions. But that's kind of the point of these office hours, right? So that's it for the questions I got asked with 10 minutes left to go. Again, if you ever have questions, please feel free to email them in advance. Sorry, checking the emails to see when they actually call it and say that we're not going to be in person tomorrow. Still not happening. Yep, still got audio too. So that's it for questions. Again, I got the chat up if you got anything else you want to ask. I'm going to switch this to the blank screen so I can get a little work done in the next 10 minutes. So yeah. All right, so again, these are office hours. These are not lessons or lectures. So if you have any questions, please feel free to email in advance or post them in chat, and I will probably not see any of you tomorrow. But again, we haven't announced that yet.